Hello everyone. So in the last lecture, we started studying about the metal carbonyls and has completed unit 3.2. So let us move forward and study about symmetry of metal carbonyls. So before this, just a small recap of what we studied in the last lecture was we studied how carbonyls can bind to any metal and what are the various spectroscopic techniques by which you can easily get to know about the various binding types of carbonyl. And also we studied that what are the various stretching frequencies of various complexes and what in what are the things that it depends upon, the stretching frequency depends upon. And then we studied the we also saw the MO diagram of the metal carbonyl, and then we got to know that from which orbital it donates, like it's a sigma donor and a pi acceptor. So all of those we studied, and we also studied about the binding modes of carbonyls, and we saw that how many different modes by which carbonyl can actually bind to metal centers. And now we are going to study about the symmetry of the metal carbonyls. So, as I told earlier also that the spectroscopic technique that is used to uh, that tells us about the different carbonyls present in the metal center is the IR. So it is very sensitive. The binding of carbon and the stretching frequency of the CO bond is quite sensitive to the electronic distribution in the metal center. So that is why it is seen in IR. Now, now we are going to actually study how we are going to see in IR, what we are going to see in IR. So actually, it depends upon the symmetry of the metal carbonyls. So how many bands you are going to, supposingly, you have three carbonyls in your metal center. Or like, for example, I'm taking just three carbonyls in your metal complex. Then there should be a question like, how many carbonyl, like if it's complex and you have synthesized that complex, you're anticipating that the complex that you have synthesized has three carbonyls. Okay, and you have also anticipated some structure of it, right? So now, or if, for example, you have to know the structure of it in both ways, actually, IR can help. So, in that case, you will what you'll do is that you'll take the IR and then you have like now you know that how many carbonyls, like how many uh, peaks of what they are there for carbonyls, right? So and from that you can get to know the structure. Okay, so how many? So that structure you can easily know, right? So that comes from symmetry of the metal carbonyls. If those carbonyls, supposedly in your complex you have three carbonyls, and all the three carbonyls have different symmetry. You know, the symmetry of the molecule is such that the three different carbon is differently oriented, like has different electronic properties. Okay, they're not similar. Then you have three different carbons, right? So actually, the number of uh, what we say, the number of different peaks for carbonyl depends upon the symmetry of the metal complex. So based on these symmetries, you can easily get to know that how many carbonyl peaks you get in IR and vice versa. Okay, so from the carbonyl peaks, you can actually elucidate some structure of the metal complex as well. Okay, and also sometimes this IR not only helps you to understand the structure and the geometry of the complex, but also tells us, for example, like in the reaction, supposedly in the first step, your one carbonyl out of three is knocking out. Then in that, after some time, you can take, initially you took the IR, you got three carbonyl peaks. And then after some time in the reaction, when the reaction was going on, you took the IR again, and then you saw that there is two carbonyl peaks. So this, what does this mean? This means that in the reaction or within the reaction, one carbonyl is getting knocked out. Okay, so this spectroscopic techniques, this IR, when we're talking about carbonyls in the metal complex, actually tells, sometimes it is very much helpful in order to know the mechanism involved in the reaction, and that is why it makes these spectroscopic techniques highly useful in organometallics and catalysis. So let us move forward and let us understand. what are the various symmetry of metal carbonyl complexes that is possible. So the local symmetry around the central metal atom of metal carbonyls decide the number and intensity of the carbonyl stretching bands in the IR. Okay, so how many bands you are going to get in IR depends on the solely depends upon the local symmetry on the about the around the metal center. The number of IR active bands possible for a specific isomer can be arrived at by using group theory. Okay, so from group theory, you can easily get to know what is the symmetry element of your metal complex. So by simply counting the number of IR bands present, one can deduce the symmetry of most of the substituted metal carbonyls. Okay, so table 3.4 shows the symmetry and the number of IR bands for common isomers of substituted octahedral metal carbonyls complexes. The same analysis is applicable to tetrahedral and trigonal bipyramidal metal complexes as carbonyls as well. So for example, okay. So for example, relationship between it is the relationship. So table 3.4 tells you the relationship between symmetry and the number of carbonyl stretching bands. Okay. So in this complex, it's a metal a homoleptic metal complex. So there is 6 carbons. Okay. So for example, for this 6 carbon, you're getting only one. How many IR bands first of all you'll get for this complex? Going like just the opposite side. So for example, you already know the structure. You can get to know. You can easily like have a rough idea like how many carbonyl stretching band you'll get. So for this, all the carbonyl is symmetrically equal, right? So it is having octahedral symmetry. Okay, so this octahedral symmetry is there, and that is why all the carbonyls are same. And now let us talk about the second one. Okay, so here what do you think is the symmetry? So it is D4. It is what it is? It is C4V, right? So from this axial position, you have the that axis. You can and this C4, that is the C4 axis, and then this is the and this axis is only the plane also. Okay, so that is why C4V. So in that case, this, this, and this. Okay. So in this, actually, it is written 3, but it is, what do you think it should be? It should be 2, right? But sometimes you get to see 3, sometimes you get to see 2. Okay. And here, for example, this is highly symmetrical, right? So for all these carbonyls, you'll get 1 because it is D4H, because there is this axial, this is C4, and then you have this plane, that is the plane of symmetry that makes it D4H. Okay, so these two L is also same. These two carbonyls, and also these two carbonyls and these two carbonyls. That means all the carbonyl is 1. So you'll get only 1. For example, if you have 4 carbonyls and it is in cis geometry, so which symmetry it is? So in this case, you will see that it is okay. It is C2V, right? So what is which is the axis over here? So this axis, for example, if you consider this CO and CO as a plane, and these two CO as the axial ligands, then this plane basically, so this line is the C2 axis, okay, and this is only the plane, so it is the C2V. So here you'll get 4. Okay, it is written over here 4, but you can also get lesser. I think you can get 2 also. Okay, these two are same, these two are same, that is why. Okay, for example, you have 3 carbonyls and it is such a way that it is in the FAC isomer. Okay, so in fact, what you have 2 same ligand in the plane and 1 in the axial position. Okay, so that makes, you can see this triangle, right? So this triangle you can easily see, and what is the isomer over here? So if you have these two and these two same, then you can easily have C3V, right? So, and if you draw the C3 axis is just coming outside of this book page, okay, perpendicularly. So this is the C3V, and you have this plane of the slide as a plane of symmetry. So it is C3V. So what does this mean? So you have how many carbonyls right here, which will be same. So these two will be 1, and this another one. So yeah, you'll have two. For example, if you have mer isomer, so in mer isomer, all the three ligands are there in the same plane. Okay. So in this case, what do you think is the plane of axis? Sorry, is this line? So this one. So if you draw the axis crossing this carbonyl, this metal, and this ligand, this is, and you rotate it in 180 degree, you will have C2 axis, and then you have the same axis as plane, then that is the plane of symmetry. So you have C2V. So here it is written 3, but I think it can be 2 also. Okay, one for this and one for this. So the number of bands expected on this is the formal selection rule, but okay, but in some cases where there is star, and I also mentioned, so few bands are observed. So in ml co whole 5, okay, this one we're talking about. So if the fold array of carbonyl ligands lies in the same plane, only two bands will be observed. In case of cis, this one, and mer, if the trans carbonyls are collinear, one band less will be observed. So basically, it also depends upon which type of ligand you are using. Okay, the L, because if it is bulky, then there is some steric repulsion, and then this particular C2 won't be followed. Okay. Now, synthesis of metal carbonates is actually also important in order to study, okay, because we know that these metal carbonyl complexes, they are used as a precursor for various metal complexes, whatever you want to prepare in the lab. Okay, so let us now understand how these precursors are made. Okay, there are various techniques by which it can be made. So all the techniques will be discussed in this lecture. So it started from 1868. So this guy, Schützenberger, prepared the first metal carbonyl compound, which was platinum-based metal carbonyl compound, by the reaction of PtCl2 with carbon monoxide. So if you, in the PtCl2, if you give carbon monoxide, which is gas, then you get to these two complexes. Okay. Now, simple homoleptic or binary metal carbonyls are made by two basic methods: direct reaction of the metal with the carbon monoxide that we studied, the first platinum metal carbonyl complex, and the reductive carbonylation, in which the metal salts react with the carbonyl in the presence of reducing agent. Okay, so if there is two methods, the first one is direct carbonylation, where you use the metal in its zero oxidation state and you like give carbon monoxide, then you have the metal carbonate. And second is the when you start with a metal salt, okay, then the metal is in some n plus state, plus n oxidation state. So in that case, that is called reductive carbonylation, because in that case, sorry, because in that case, the oxidation state of the formed metal carbonyl needs to be decreased. It should be zero sometimes. Okay, if you have homoleptic, we're talking about homoleptic carbonyl complexes, for example. So homoleptic carbonyl complexes, where the complex only have carbonyl ligands, it has to be, the oxidation state should be zero in order to maintain the stability as well as the neutrality, right? Because carbonyls are neutral L-type ligands. So in that case, you have to do the reduction. That is why the name is reductive carbonylation. So the direct carbonylation we are going to study. So this method is applicable to the synthesis of only a few metal carbonyls. For example, nickel carbonyl whole 4 is the classic example, which was discovered by L. Mond's process, right, in 1890, and has since then been utilized in the refining of nickel as well. So refining of nickel is Mond's process, right? So this is what he's observed. So when you give, when in the nickel, when you have 4 equivalent of carbon monoxide in 1 bar pressure and 25 degrees centigrade, you get nickel carbonyl whole 4, which is colorless, and the melting point of it is minus 17 degrees centigrade. That means what? It means it is liquid, right? And also, okay, fine. And the boiling point is 42 degrees centigrade. So if in summers it exists as gas as well. Okay, and this iron carbonyl is made in the similar way. It is a pale yellow, again liquid at room temperature. Now, reductive carbonylation is a very interesting technique, and there's quite a lot of examples given in this book. And not all the examples we are going to discuss. We are only going to discuss few, okay? Because they are similar. So, reductive carbonylation is the most commonly utilized method for the preparation of binary metal carbonates. Now, reducing agents such as aluminum, sodium, zinc, trialkyl aluminum, and grignard reagents are used in the reaction with a metal halide or a acetate along with carbon monoxide at high pressures and temperatures. Okay, so because here you need to change the oxidation state, so you need some high pressure temperature conditions. So, for example, the first one, in order to make the homoleptic chromium carbonyl complex, octahedral this is, then you need to take chromium chloride, and this is the reducing agent over here, aluminum. And you used to, how many carbonyl you need? 6, right? So you have 6 equivalent of carbon monoxide. So in benzene, so this is benzene in AlCl3, which is a Lewis acid at 300 bar pressure and 140 degrees centigrade, you get the homolytic carbonyl. Okay, so similarly, you can actually go through each one of this. So you need a metal precursor, you need a reducing agent, and you need a carbon monoxide with high bar and temperature. Sometimes the temperature is negative as well. So it depends. In different solvents, you can get the metal carbonyls. So in some cases in the case of metal oxides, carbon monoxide itself acts as a reducing agent and gets converted to carbon dioxide in the process. So the reaction conditions are selectively more drastic for such reactions. So, for example, if certain metals that exist as oxides, so in that case also you can make the carbon monoxide, and in that case you don't need some external reducing agent. Here, carbon monoxide only acts as the reducing agent itself and gets oxidized to carbon dioxide, and thus forming the homoleptic carbonyl complexes. Okay, so for example, osmium oxide, rhenium oxide, ruthenium oxide, cobalt, iron, molybdenum oxide, and all of these is listed over here. And in this case, even more drastic temperature and pressure conditions you need. So there are also a variety of other methods. However, they are specific to a few metal carbonyls clustered and industrially useful carbonyls. So these are some of the carbonyls that are very, very useful in the industry point of view, because these carbonyls, they actually act as catalyst itself, but also as a metal precursor, and is used quite a lot, right? So all of this is listed over here. For example, in order to get iridium carbonyl, so this is the method, okay? So here you have iridium, another is again a complex only, and then you have to use carbon monoxide in methanol, you have to reflux at 1 atm pressure. So in order to get some this rhenium carbonyl, so you need rhenium trichloride, okay? All of this is mentioned over here. Now let us talk about a very important topic of this chapter, which is the reactions of metal carbonyls. So I'm going to focus on this topic quite a lot and deep, because this is something that is actual organometallics and will be useful quite a lot in solving various reaction mechanisms. So these are the very basic in this topic. The topic is going to discuss the very basic steps that is involved in big reaction mechanism. So let us start. So reactions of metal carbonyls, and we are going to study how metal carbonyl actually reacts, and what are the various ways in which it reacts, and what is the mechanism. Everything we are going to study, and how you can activate any metal carbonyl, all of those. Depending upon whether the metal carbonyl is an 18 electron species or not, dissociative or associative pathways are observed in substitution reactions. Okay. For example, a 16 or 17 electron containing metal carbonyl can react by an associative mechanism. Okay, because there in the 16 or 17 electron metal complex, you already have vacancy. Okay, so that in that such metal carbonyls, the reaction can go via associative pathway. But for example, if your complex is 18 electron, so in that case, this electron is already filled, okay? So the coordination is filled, it's full, and so the reaction, whatever you're reacting with the metal carbonyl cannot go via associated pathway. In that case, one of the carbonyl needs to be uh, knocked out of the metal center, and that way it is called dissociative mechanism. Okay, so it is written also over here. It okay, and it will be much faster than the reactions on a 18 electron metal carbon, which proceeds via dissociative mechanism. And by dissociative mechanism, we already discussed it right now. Now, substitution of carbonyl groups under thermal and photochemical condition constitutes the most common reactions of metal carbonyls. Now, in addition, reactions such as disproportionation, oxidative decarbonylation, and reductive and addition of nucleophiles of the metal carbonyl can also be carried out on metal carbonyl. So all of these reactions we are going to study. Okay, the disproportionation, oxidative carbonylation, reductive and reduction and addition of nucleophiles, all of this. So first of all, let us start with uh, the topic which is known as the activation of the metal carbonyls. Okay. Lewis bases, olefins, arenes are some of the ligands which can be thermally substituted on the metal carbonyls. Okay, okay. Now, a complete substitution of all the carbonyl groups is rarely accomplished. Okay, you cannot substitute all the carbonyl, which is it's really impossible. You can substitute one or two carbonyl, that is enough, because these metal carbonyls, as soon as you remove one carbonyl, so the back bonding to other carbonyls further increases in the metal center or the metal complex, which makes the metal carbonyl bond even stronger. So knocking out all the carbonyl is a tough thing to do. Okay, you can knock out 1, 2, 3 max to max, but more than that, it is very difficult. Okay, you need to apply a lot of energy. Now, there are few ligands they have mentioned. For example, some Lewis bases, some olefins, some arenes, which can be easily added to the metal carbonyls. Okay, by using high temperatures, definitely. So, a complete substitution of all the carbonyl groups is rarely accomplished. One method that is usually adopted is the activation of the metal hexacarbonyl by the intermediate introduction of a relatively more labile ligand, which is replaced later by another ligand under mild condition. So some of the metal carbonyl transfer reagents are these. So for example, in this cases, what they have mentioned is that, for example, what you do is that you replace one carbonyl with a labile ligand. Okay, so labile ligand. So these are prepared by the direct reaction of the homolytic metal carbonyl with a solvent for reagent under thermal photochemical conditions. So easily, when you give one like thermal for example, in the thermal condition, you can knock out one carbonyl, which is quite easy to knock out, okay? And you can replace one carbonyl with some different, more labile ligands than carbonyl. Okay, carbonyl is not labile, that much it is not labile, because it's a pi-acid ligand, okay? There's a double bond like character between the metal and the carbonyl, so hence it is not called as labile ligands. But easily you can knock out one carbonyl and put even more labile ligands in order to activate the metal carbonyl. For example, this homolytic carbonyl complexes, that is the chromium, in at minus 30 degrees centigrade and 100 minutes in THF. For example, we are giving THF, and this is light, which is 150 watt light. What you can do is that you can knock out one carbonyl and get THF in place of one carbonyl. Okay, thus activating the metal carbonyl complex. And similar way, this alkene moiety can also this can actually knock out two, because there is two binding sites. Okay, and if it is binded by two binding sites, then it makes a chelated complex, which is far more stable than the non-chelated complex, and that is the driving force here to knock out two carbonyls. But for this, you need a reflux condition for 9 hours. Okay, again, this if you use acetonitrile, so acetonitrile is also quite labile ligand, also a small ligand. So it can, in reflex condition, it can knock out three carbonyl and get three. Okay, but more than three, it is quite impossible. And once you get rid of three carbonyl, then what you can do, and this you know already that the acetonitrile ligands are very much stable, so you can easily then substitute this three ligands that you just incorporated the nitrile ligands by some other ligands. For example, in equation 3.30, they have replaced it by one benzene. Okay, at 25 degrees centigrade. So it's very easy to do it, right? But it was very difficult to get rid of carbonyl. You need it to flux condition. But in order to get rid of this acetonitrile, you don't need any reflux condition. Room temperature works. Okay, so this is the various modes of the activation of metal carbonyls. Now, the second reaction that we are going to study under metal carbonyls is the disproportionation. So let us study what disproportionation is actually. So disproportion, whenever we hear this word disproportionation, so what comes to anyone's mind is that there's a loss and a gain of electron in a reaction simultaneously. So that is what disproportionation means, right? So some multi-metal carbonyls can undergo disproportionation in the presence of suitable ligands, often leading to carbonyl anions. Okay. So here you have manganese 2 CO holes. Then we already know the structure of this manganese carbonyl. We know that it forms dimer. Okay. So in this chapter only in the first figure it was mentioned. The structure of this complex was already mentioned. Now, if you give pyridine, then what can happen? Pyridine is also a strong sigma donor. So in that case, there's a chance that uh, the manganese, okay, there's a so it is a dimer. So this dimer can break and actually form a anionic complex and a positively charged complex. Okay, so we know that in case of anionic complex, the metal carbonyl will exist because in case of anionic complex, the metal to carbonyl bond is even stronger. But the cationic complex, the metal carbonyl bond is not that strong, and that is why here pyridine is substituted. Okay, so this also requires quite high temperature, 120 degrees centigrade. So this is disproportionation. Now, nucleophilic addition to carbonyl. It is also very important in terms of organometallics. Now, nucleophilic addition to the electron deficient carbon atom of the metal coordinated carbonyl group has become a powerful tool in the organometallic chemistry. It is commonly called the Haber-based reaction. Fischer carbines can be prepared by the addition of alkyl lithium to metal carbonyls followed by the methylation. Now, carbines are important reagents as well as catalysts for the host of organometallic transformation. So what they have done here is that, so you have this homolytic metal carbonyl, and when you use alkyl lithium in ether solvent, then what happens? You know, this is negatively charged, this is positively charged. So this negatively charged entity can easily substitute it. So this is carbonyl. So carbon is delta positive. Okay, it is also donating its electron to metal, so that is why it is delta positive, right? And this oxygen is delta negative. So this R negative can easily it's a nucleophile, can easily attack to this electrophilic carbon center and then can form this type of moiety. Okay, and further, if you add this Me3O BF4, then what actually can happen is lithium can be substituted by methyl. So this is what is called the nucleophilic addition to carbonyl. Now, electrophilic addition to carbonyl is also possible via oxygen because oxygen is delta negative. We just studied in the last topic. So, Lewis acids such as ALET3 can attack to the oxygen end of the coordinated carbonyl group. Only bridging carbonyl groups are nucleophilic enough to undergo this reaction as far as metal carbonyls are concerned. So, the addition of electrophiles become more facile with anionic carbonyl metallics because as in negatively charged complex, the donation of electron from metal to carbon is quite high, and that is why which makes carbonyl oxygen even more delta negative, and that is why it can easily bind to the Lewis acid, for example ALET3. And if also if the carbonyl is bridging carbonyl, then in that case also the high back donation is quite high, so which makes the oxygen even more delta negative. So one example is given in equation 3.33, which is written over here. So this is the bridging carbonyl, and then there is terminal carbonyl as well. But when you use ALE3 to equivalent, then it only get to the bridging carbonyl first, not terminal carbonyl remains like that. Now different type of reaction we are going to study is the carbonyl, anion, and cation and hydrides. Okay. So carbonyl anions are also formed by the reduction or by the reaction with stronger nucleophiles. So for example, you have stronger nucleophiles over here. Now you have okay, fine. Okay, so now in this equation 3.34, 3.35, and 3.36, you're actually activating the metal carbon. Okay, so you're getting the anionic complex of the metal carbon, corresponding metal carbonates, and those carbonyl anions are stronger nucleophiles. Okay, and can actually then take part in the reaction to further react. Now, for example, this manganese cobalt dimer can react with sodium metal to form this anionic complex, Na manganese carbonyl 4 5. Okay, so this is a one example. Another example is the cobalt dimer. So here also, when you react with sodium, you get the anionic carbonyl complex. And same happens with the iron also. So while reduction with common reducing agents such as sodium, so all of these are reducing agents because what it is doing is giving one electron, one or two electron actually providing electrons to this metal carbonyl complex. So that is why they are highly reducing, right? Reducing agents, good reducing agents. So while reduction with common reducing agents such as sodium amalgam results in a mono or dianionic species with stronger reducing agents such as sodium in liquid ammonia or sodium with HMPA, they can be further reduced to the former oxidation states of the metal, reaching even -4. Okay, so if you further, so this is -1. Okay, further, if you this is even more stronger reducing agent, sodium and HMPA combination, so you can actually have this species as -3. Okay, so you can further induce that ionic thing, the stronger reducing agent. Now, carbonyl cations are prepared mostly by, so we saw that how carbonyl anions can be prepared. Now, carbonyl cations, how you can prepare? So, you can prepare by oxidative carbonylation. So, in that case, Lewis acid in anhydrous HF or superacid such as HFSB5, along with an external oxidant. So, you need for that, in that case, oxidizing agent. So, you need some external oxidant are found to be ideal for the releasing realizing the carbonyl ions. So if you have this iron carbonyl whole 5 in the presence of zinc fluoride and SbF5, okay, in carbon monoxide 180 pressure, you can easily form this positively charged carbonyl complex entity. Okay, but for all of this, you need some Lewis acid. So here it is. Here there is PF3. Okay, carbonyl hydrides are prepared from carbonyl hydrides are prepared from carbonyl anions, carbonyl halides, or endimeric carbonyls. The term hydride is assigned based on the formal oxidation state. However, the properties of the organometallic hydrides vary from hydridic to protic in character. Based on the nature of the metal and the ligands, the acidity of these complexes varies significantly. Now, synthesis of carbonyl hydride complex. How can you get it? So definitely, if you have this anionic complex, which we know how to synthesize using various reducing agents like sodium, potassium, all of those metals. So if you add this H positive, then you can form this complex, which is a metal hydride complex. Okay, there is a direct bond between the H and the metal. That is called the metal hydride. So similar it is given for iron as well. So if you use sodium borohydride, you can actually make the metal hydride. In case of manganese, if you give hydrogen some pressure, then you can find from the metal hydride. In case of iron also, if you have this hydroxyl anion, then you can also form this metal hydride bond with the whole negative charge. Now this is the last topic which we are going to study in this lecture, which is the Coleman's reagent. It is quite important reagent. Okay, so first of all, what is the Coleman's reagent? You need to know. So this is this sodium 2FeCO4. Now we know that how do you make this compound, right? So this is called the Coleman's reagent. So it is Na2FeCO4. This is the Coleman's reagent. Has found many applications in organic synthesis. Organic halogen compounds can be functionalized in many ways via reactions with the Coleman's reagent. So this is the Coleman's reagent, and if you use some halide, organic based halide, then what can happen? This R can be present. So the metal alkyl or there's an organic bond formation. So metal and then some organic group is there. Okay. And then further, if you give more carbonyl, then this carbonyl insertion can take place between the metal and the alkyl bond. Okay. And once if this is formed, then if you give the acidic medium, then you can form the aldehyde, and if you give some halogens, then you can form this carbonyl halides. Okay, so this is very reactive intermediate. And also, if you give some organic based halides, then you can form ketones. If you give oxygen, you can form in the acidic medium, you can form acid. Okay, there are various uses of Coleman's reagent. So this various important terms which is given over here from the topic 3.57, 3.5.7, which is migratory insertion of carbonyls followed by oxidative decarbonylation, photochemical substitution. All of these will be covered in the next subsequent lectures, because these are very important topics, and actually you will come across all of these reactions in almost all the mechanism. So because we know that many metal complexes have carbonyl as one or two like has it as carbons as ligands. So I hope that this video is useful for you, and so thank you.